Today we are going to be talking about limited resource allocation. In our last lecture, you would recall we had talked about the problems of resource aggregation and the problems of resource leveling. Now, as you know, the objective in resource leveling was to be able to smoothen the resource usage profile so that it was as well leveled as possible. Today we are looking at the limited resource allocation problem, and if you look at the problem, the essential problem and how it differs from resource leveling is, in resource leveling what we are trying to do is we are trying to obtain a favorable resource usage profile without worsening the project duration T. But what may happen is that even the best leveled resource profile might exceed the limited resource availability. So, if this happens, obviously this schedule would not be easy to implement, because during this particular time period you would be exceeding the resource availabilities that you have. So, you would have to make special provisions either to hire additional resources or to make some other arrangements of subcontracting and so on. Now, if this was not possible, we would have to look for means by means of which we could accomplish the project within the limited resource availability. So, the essential problem in limited resource allocation is to be able to find out which are the activities which are going on during this particular period, and maybe to defer them beyond this peak, so that the new resource usage profile actually conforms to the resource restrictions that we have. And in this process, inevitably the project duration increases from the original value T to this particular new Ti, the increased value of the project duration. Now, the major problem in resource allocation is to be able to determine this resource usage profile in such a manner that this increase in duration is the minimum. So, essentially this is an optimization problem in which we are interested in finding out the minimum project duration subject to the availability of resources. There could be not only one resource, but there could in fact be multiple resources, and we are trying to find out a particular value of the duration such that all the resource availabilities are satisfied. So, essentially this is the problem, as opposed, mind you, resource leveling is often referred to as unlimited resource leveling, because there we are not specifically concerned with the availabilities of the resources. Now, the limited resource allocation problem there are essentially two ways of looking at the problem as far as the solution techniques are concerned. There are, number one, the optimization procedures which guarantee an optimal solution, and some typical examples of these are, they are generally some LP based formulations in which constraints are imposed saying that the precedence restrictions are met, that the resource availabilities are not violated in each period. So, constraints are written for these individual constraints, and then the formulation is solved. The other approach to optimization procedures is enumerative and integer linear programming approaches. See, essentially the problem of determining a project schedule is a combinatorial problem essentially. Why is it a combinatorial problem? Simply because there are many possible options for the starting date of a particular activity. So, whenever you look at all the possible combinations of starting dates of various activities, you get a variety of schedules, and therefore it is essentially an enumerative technique, and in fact a lot of refinements in enumerative algorithms have been proposed, especially by using some branch and bound techniques and searching over a tree. And of course, there are other procedures which are based on analogies. There is a very interesting network path, that means developing a network and trying to find out the shortest path in that network by drawing an analogy between the assembly line balancing problem and the limited resource allocation problem. But the difficulty with all these approaches is that they are not good for real life, real sized problems. They are typically demonstrated to be good for problems which may involve, let us say, 10 or at most 20 activities, because the size of the LP formulation or the size of the enumerative number of solutions becomes very, very large, and therefore it is not possible to use these procedures for real life situations. So, although these particular procedures have been useful in research, and a lot of research has been done on these procedures, they have not found their way into practical algorithms or in commercial software which is generally used for these kinds of purposes. The commonly used procedures are essentially heuristic procedures, and one way to classify these procedures is serial approaches and parallel approaches. These differ in terms of how the heuristic is used to basically select out of the many possible combinations the one particular combination that is to be scheduled. Let us now examine some of the typical problems with heuristic procedures and the kinds of approaches which are available. The limited resource allocation problem in projects is a combinatorial one that we have already mentioned. By this what we mean is that there are a large number of combinations of activity start time satisfying both precedence and resource constraints. So, these combinations exist, and because of these large combinations you have a large number of heuristic procedures possible. What do these heuristics do? You know, the word heuristic simply means a rule of thumb. So, a rule of thumb is actually used to establish activity priorities in these schedules, and these produce good rather than the best solution, as we have seen. Now, talking about the two broad categories of heuristic procedures, namely serial and parallel procedures. Serial procedures are essentially those procedures in which all activities of the project are ranked in order of priority as a single group and then scheduled one at a time, that is serial. So, really speaking, what happens in serial procedures is that you establish the priority of the job only once, and you do not change it during the course of the application of the algorithm. So, it is something like you say activities are born with, it is something in their genes. The moment you pick up a project, you can identify the ranks of the activities, and these ranks stay with them as long as the activities are being scheduled during the particular process. This is what is being done. As opposed to this, we have parallel procedures. In parallel procedures, what happens is that all activities starting in a given time period are ranked as a group and the resources are allocated, and at each successive time period a new rank ordering of all the eligible activities is made and the process continued. So, the key difference really between serial and parallel procedures is that in the parallel procedures, in each period you set up a competitive examination, as it were, and you allow the activities to perform on that, and it is on the basis of their karma that the individual activities perform, and you make a selection based on that. So, in each activity the activity can in fact improve its ranking or maybe worsen its ranking depending upon the situation. Now, out of these two kinds of procedures, parallel procedures have proved to be more efficient generally than serial procedures, and we will take a look at one such parallel procedure during the course of this particular. Now, there are a number of commonly used heuristics. Now, here is a partial list of these heuristics. Minimum activity slack is perhaps one of the most commonly used heuristics. That means if an activity is critical, it should be given greatest priority. If it is less critical, it should be given lesser priority, and so on, and this is determined by the total float of the activity, which is, I think, intuitively quite obvious. The minimum late finish time of an activity is another criterion which is quite commonly used, and it is shown that both these criteria are actually one and the same in terms of their application. A resource scheduling method has been proposed in which a priority is given to a particular activity based on its early start and the late finish time of the activity. So, you can attach some weights and then you can develop a priority sequence for the various activities. The greatest resource demand, what this really means is that suppose there are 3 activities competing to be scheduled on a particular day. The activity which has the greatest resource demand, which requires the maximum crew for instance, would be the one which would be picked up by this particular heuristic. Then we have the greatest resource utilization. Now, greatest resource utilization means that whenever there is a set of activities which has to be scheduled, you try to pick up a subset of these activities in such a manner that the maximum amount of resource is scheduled. So, it is like trying to pick up, it is like a typical classical knapsack problem in linear programming, where you are trying to pack a bag with the maximum value, assuming that each item which you have to pick up has the maximum value subject to the resource availability, that is the capacity of the bag, right. So, out of the various, so the asterisk here shows this. So, what can be done is a small LP can be solved to determine which particular combination of activities will in fact give you the greatest resource utilization. The shortest imminent operation, out of the various activities, the one which is likely to take the shortest time is given a priority here. This is a rule which has performed very well in job shops, especially because it leads to low inventory levels. But as we will see, this does not perform so well in project scheduling. Another heuristic which is quite often used in scheduling of projects is most jobs available possible. Most jobs possible mean that if there is a list of let us say 5 jobs and all the 5 cannot be scheduled because of resource availabilities, you try to pick up a schedule in which the maximum number of jobs is scheduled. So, maybe 3 or 4 if they can be picked up, that can be done. This again can be set up as a linear programming problem, and you can identify the set of jobs which should be picked up. And of course, another very commonly used heuristic is random activity selection, where out of the various jobs one can be selected at random, and you can do this. So, in one particular study these 8 heuristics were compared, and it is interesting to see the results that were obtained. If we look at these 8 heuristics and we find that this is a ordering of the heuristics in terms of the percentage of problems for which the optimum was found. It was found that the min-slack heuristic for that set of problems led to an optimum in 29% of the cases, LFT in 20% cases, RSM in 14% cases, GRD greatest resource demanded in 13%, random in only 5%, greatest resource utilization in only 2%, most jobs possible in 2%, and shortest imminent operation was in fact only 1%, which was the worst performance as far as this was concerned. Of course, since these rules did not give the optimum for the same set of problems, it showed actually for the entire problem set optimal solutions was obtained in 40% of the cases by the application of one or more rules, and for 60% of the cases non-optimal solutions were found out by the heuristics. That gives you an idea about the performance of these heuristics. Another study was done on how bad or good these heuristics were in terms of their capability to give an optimal solution. So, the percentage increase above the optimal duration was this is the increasing order. So, what we found in this particular situation was min-slack. What you can see from this graph is something like this, that the random rule, which is it gave a percentage increase above the optimal duration of about 11.4%. So, this was the kind of performance of the random rule, and all these rules had been arranged in this fashion. So, really speaking, as a general indicator, you can see that these are the 3 rules which are better than random, and these are the 4 rules which are worse than random. So, really speaking, the min slack rule gave an increase in optimum duration of only 5.6% above the optimum, LFT 6.8%, RSM 6.8%. So, they were fairly close and pretty good and better than random. And then if random is taken as a boundary, these were all much higher, 13.1%, 13.1 and going up to 16%. So, this could be a kind of a guideline as to which particular rule. Obviously, the conclusion here is that rules based on min slack or latest finish times are generally performing the best as far as the heuristics are concerned. So, we will now take up heuristic procedure suggested by Wiest for resource allocation. This particular procedure of Wiest is based on very simple 3 rules of thumb, and these 3 rules are the following. The first rule simply says allocate resources serially in time, that is go from one day to the next day, that is start on the first day and schedule all jobs possible, then do the same for the next day and so on. So, basically what we are doing is we are moving from the first day to the second day to the third day and so on, very simple. That is the first heuristic. The second heuristic says that when several jobs compete for the same resources, give preference to the jobs with the least slack or the least total float. So, what we have what we are trying to do here is that we are using the heuristic of least slack to pick up the jobs. And third one is a slightly interesting rule. It says try to reschedule non-critical jobs if possible to free resources for scheduling the critical jobs, which means that at any particular stage, if a situation occurs when a non-critical job is already scheduled, but there is a critical job which is demanding some resources, if it is possible to sacrifice the non-critical job, then try to do it in favor of the critical job if possible, otherwise no, right. So, these are simply we call it rule 1, rule 2 and rule 3. These are the 3 heuristics on which the Wiest procedure is based for resource allocation. Now, what we will do now is to look at a small problem and try to apply these 3 rules to that problem systematically and try to see how we can obtain a solution to the limited resource allocation problem. First, let us state the problem. Let us take a network which has 10 jobs. You can see that jobs are numbered 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So, there are 10 jobs in this network, and the number of the job also indicates the crew requirement of the job, right. For instance, job number 7 requires 7 men, this job number 1 requires 1 man, this job 4 requires 4 men and so on. The durations of each of these activities are actually indicated on this time scaled network. For instance, 7 takes only 1 day, 1 takes 4 days, 4 takes 3 days, 3 takes 2 days, 5 takes 2 days, 6 takes 2 days, 2 takes 2 days, 9 takes only 1 day and 10 takes 3 days. So, we have developed in this particular case the early start schedule for this particular project. All activities are scheduled at their earliest. So, these dotted lines show you actually the amount of total float which is available to the various activities. For instance, activities 1 and 8 have a total float of 3, activity 5 has a total float of 1, 2, 3, 4 days, right? And in fact, in this particular case, there are two critical paths, 7, 4, 2, 9, 10. This is one, and 7, 3, 6, 9, and 10. These are the two paths which are critical. And if we find out, so the project duration without any resource restrictions is now 10 days, as you see here. And you can do a resource aggregation exercise and see that the total resource requirement is 7 on the first day, 13 on the second day, 13 on the third day, 11 on the fourth day, 9 on the fifth day, 16 on the seventh day, and 17 on the seventh day, and subsequently 10 on days 8, 9, and 10. So what you find is that the peak resource requirement is 17, which occurs on the seventh day, and this is in fact the problem data as it is. So the unlimited resource allocation problem will give us this. Now for this particular problem, what are our requirements? The requirements are stated as follows. The unlimited resource early start schedule has a peak crew requirement of 17 persons on the seventh day, as we have seen from this example. The maximum crew availability is only 10. That's what we are seeing. And the application of a resource allocation procedure is therefore necessary to obtain a feasible schedule within the limit of 10 men. Obviously, I think for this example, it is easy to see that you cannot find a schedule with less than 10 men, because there is one particular job, that is activity 10, which requires 10 men. So the maximum resource requirements of any activity in a particular project will in fact be the lower bound on the resources needed for that particular job. Of course, there would be other factors as well, but in this case we are looking for a schedule with only 10 men. So what we do is, we keep this original problem in mind, which defines our structure, which defines our precedence relationships. And what do we see in this problem? We find that there is only one activity which has no predecessors, and that is activity number 7. So this particular activity is the only candidate on day 1 for scheduling, isn't it? So what we do is, we proceed systematically as per the first heuristic, day by day. So on day 1, what happens is, on each day we construct a list of eligible set of jobs and their total floats. We find that job 7 is the only eligible set of jobs because it has no predecessors, and it has a total float of 0 because it's a critical job. And this job can be scheduled leaving 3 units of unutilized resource, because there is nothing else, no other job, so this job can be scheduled. So the decision on the first day obviously is this. On the first day we will now build up the schedule day by day. On the first day we take a decision that we schedule the first this particular job 7, and once we schedule this job on this particular day, on the first day the total crew that we have used up is 7, and that's what it is. And after this we move to day 2. Now as you move to day 2, job number 7 has a duration of only 1 day, so job number 7 would be over. When job number 7 is over, all the successors, all the immediate successors of 7 become candidates for placement on the eligibility list. So let's find out the eligibility list on day 2. Mind you, we are doing a parallel heuristic. So on day 2 we have these 4 jobs, 3, 4, 1 and 5, which have now become eligible for placement, and we order them first according to their total float, because this is going to be our tie breaking heuristic. So 3 and 4 are both critical jobs, they have a total float of 0. Job number 1 has a float of 3, right? You can see, for instance, job number 1 has this float of 1, 2, 3. Both 1 and 8 can be slided by 3 days. And job number 5 has a float of 4 days. So this is the order of the jobs. Now we have to allocate a total of 10. When we'll pick up in this order. So 3 plus 4 is 7, plus 1 is 8, and this cannot be scheduled, right? So what we do is activities 3, 4 and 1 can be scheduled, leaving 2 units of unutilized resource. That means 8, 4 plus 3, 7 plus 1, 8 units of resource would be consumed. That is, the crew consumed would be 8 in number, and 2 units of unutilized flue would be left over. Now out of these, if you see, job number 3 has a duration of 2 days. So since job number 3 and job number 4 has a duration of 3 days, job number 3 has a duration of 2 days, and job number 1 has a duration of 4 days. Obviously the first job to be completed out of this will be job number 3, which takes only 2 days. So since this is started in day 2, it will be over in day 3, right? That's what it means. Let's look up the situation as to what would change on day 3. On day 3, when you look at the whole thing, 3 is ongoing job because we had scheduled it in the previous period. 4 is ongoing and 1 is ongoing because these were the 3 jobs that were scheduled earlier on day 2. This was a critical job, this was a critical job, and this particular job had a float of 3 days. And 5 now has a float which is 1 day less than what the previously. It previously had a float of 4 days, but now it has a float of only 3 days because we have already postponed the start of 5 by 1 day, right? So this is what has happened. So on this particular day, clearly no additional job can be scheduled on this because this cannot be accommodated with these ongoing jobs. So as far as day 2 and 3 are concerned, on 2 we took a decision. On day 2 we took a decision to schedule 3, 4 and 1, and the implications of that decisions would be felt in the future depending upon the durations of these activities, because we have now committed resources to these activities by virtue of the decision that we have taken on day 2. And on day 3 these are continuing as things are, and therefore the partial schedule for day 2 and 3 would be something like this, and even on day 3 we are actually consuming 8 units of resource, right? So let us see what would happen now and when we come to day 4. Look at day 4. On day 4, what has really happened is that job number 3 is over, but job number 4 and 1 are ongoing. So 4 is ongoing and 1 is ongoing by virtue of the previous decisions taken on day 2, right? And this is a 0 and this is a float of 3 days, job number 1. And what has happened now is job number 6 becomes a candidate for placement. 6 is the immediate successor of job number 3 and it is a critical job. And job number 5 is has now a float of only 2 days. It is reduced by 1 more day, right? So this is the list, ordered list that we have. These are 2 ongoing jobs, and here is a critical job. The critical job is clamoring for resources, and at this stage we can invoke heuristic 3, rule number 3 of Weist's procedure, because what we notice is that here we have an instance of one job which is actually a non-critical job, which is consuming 1 unit of resource only, but here is a critical job which is asking for resource and is cannot be accommodated along with this. So if we give up 1, then 6 and 4 can be accommodated within the resource availability of 10 days, right? So that is what the third rule says, that here if this is possible, let us try to do that. So here we reschedule job 1, that means job 1 which was being done, we sort of forget about it, take it off, and we try to reschedule the critical jobs 4 and 6 on site like this. So if that happens on day 4, what are the decisions? Let us try to depict on day 4 the decisions that we have taken. So the situation on day 4 is, one which was done earlier, we have forgotten about it, we have taken it off and we say okay, it can be done some other time. Earliest it can be done is in day 5 now, but on day 4 we have rescheduled, we have scheduled job number 6 and job number 4 is already going on. So the total resource requirements are 10 and we have updated the crew requirements here by virtue of the fact that one has been rescheduled to 7, 7 and 7. So this is the change that is made on day 4. Okay. So on up to day 4, the partial schedule shows that activities 7, 3, 4 and then 6 have been scheduled, and on day 5 we will see what can be done about the various jobs which are candidates for placement. On each day you have to maintain a list. So let us now look at day 5. What happens on day 5? You see, on day 5, as you can see from this example, from this partial schedule, that job number 4 is going to be over. So the moment job number 4 is going to be over, job number 2, which is the immediate successor of job number 4, would become a candidate for placement on the list, and it being a critical job, it would in fact be it would ask for greater place. So on day 5 our situation is something like this. 6 is currently ongoing, it's a critical job. 2 is a critical job, so we place it here, and 1 is a postponed job. I mean, it was earlier it had a float of 3, but now if 1 is kept the way it is, then it is postponed to day 5. If 1 is the earlierly postponed job, it will become a critical job at this stage, and 5 has a float of only 1 at this stage. You see, 5 has become, it had a total float of 4, gradually we have been postponing it on every day, and therefore its slack has become lesser and lesser. So a stage would come when it would become critical and would become top priority in that sense. So at this particular stage, what we do is simply 6 is ongoing and 2 can be accommodated. This is also a critical job. So 6 plus 2, 8 plus 1, 9. We will try to schedule all these 3 jobs. So thus we can schedule 2 and 1 over and above the ongoing job 6 on day 5. That is what we will try to do. And on day 6, what is going to happen? Day 6 again, nothing very significant is going to happen, because 6, 2 and 1 are the jobs which were scheduled earlier. So they would now be ongoing jobs on day 6. They would be critical jobs, and at this stage job 5 has also become critical, right? Job 5 has become critical, and these are 3 critical jobs going on, but we cannot accommodate this critical job. So at this stage, so on day 6 we are forced to postpone the critical job 5, thus increasing the project duration to 11 from the original 10. So this is what happens whenever we take a decision to postpone a critical job, the project duration increases by 1 day. And that is what happens here on day 6, because we had no other option. So it's because we are now postponing job number 5, which is in fact a critical job, therefore the project duration increases from 11 increases to 11 from the original value of 10. At this stage, based on the decisions in day 5 and 6, let us see what our schedule, partial schedule looks like. So now you find that on days 5 and 6, the decisions were 6 and 2 are ongoing, and we had scheduled 1 also in parallel, and 1 will have a duration of 4 days like this. So obviously during days 5 and 6, the total resource requirement will be 9 and 9 respectively, and this is what is going to continue at the end of the 5th and the 6th day. Now when 2 and 6 are completed on the 7th day, we would find that the successors being successors to job 2 and 6 is job 9, would also become a candidate for placement, right. So, let us see how that happens. So, let us update the list on day 7. Look at day 7. 1 is ongoing. It is good to write down ongoing here, because that tells you that these resources are already committed and you have only 9 more resources to accommodate the other jobs. So, at this particular case, job 1 will have a total float of 1. Why does it have a float of 1, whereas earlier it had a float of 0? Because now you have postponed a critical job. So, your project duration has become 11. So, which means the float of all the jobs has increased by 1 day. That is what has happened, except the critical job, which is 0. 5 is now a critical job. So, it has a float of 0, and 9, job number 9, which was earlier a critical job, now has a float of 1, right, by virtue of the increase in duration of the jobs. So, our list is like this. So, thus on day 7, job 5 is, because this is a critical job, it has to be scheduled, and once it is put along with this job cannot be scheduled. So, job 5 is scheduled along with job 1, utilizing a crew of only 6. So, that is the decision that we take on day 7. Is that clear? So, we have now decided to schedule 1 and 5 together, and 9 will have to wait. So, let us see what happens on day 8. How does the list? You see, it is a dynamic list. Each day the priorities keep changing. If you have not looked after a particular job which has been crying in the past, it becomes more and more critical, and at a certain point of time it asks for attention. That is the kind of thing. On day 8, job number 5 is ongoing, job number 1 is ongoing. This has a float of 0 and this has a float of 1. And 9 at this stage, because we did not schedule 9 in the previous page, it has now become a critical job. So, here for the second time, what happens is on day 8, we cannot accommodate job 9 along with these 2 jobs, and nor can we reschedule 1, because it will not release enough resources to accommodate job 9. So, even rule 3 will not help us. So, here for the second time, we are forced to postpone a critical job 9, increasing the duration of the project to 12 days from the original 10 days. This is what has happened. So, you know, whenever you take a decision to postpone a critical job, like we are doing this for the second time in this procedure so far, the project duration has now increased from the 11, the value 11 that he had to 12. It has increased by 2 days from the original project duration. So, based on these decisions that we have taken on day 7 and 8, let us see what the partial schedule is like. So, you can say that on days 7 and 8, we have taken these decisions basically to schedule job 5 along with job 1. So, really speaking, the crew requirement is 6 and 6 on both the days, and we have been able to build up the schedule up to this particular point in time, where we know that the total crew availability touched a figure of 10 on the 4th day, 9 on 5 and 6 days, day number 5 and 6, and thereafter it is being controlled within this particular figure as shown here. So, on day 7 and 8, we see that job number 1 and job number 5, both of them are going to be completed at the end of day 8. So, when you go to day 9, what happens? Let us see what happens at the end of day 9. On day 9, the 2 jobs which are eligible are number 9, which is now a critical job with a project duration of 12, and job number 8, which has a total float at this time of 2. If you recall, job number 8 was a successor of job number 1, but at this stage therefore it has a total float of 2 with this. So hence we schedule job number 9 on day 9, and subsequently what's going to happen is 9 only takes 1 day, right? 9 is a job which has only a duration of 1 day, and subsequently what's going to happen is that job number 10 on days 10, 11 and 12, which is takes 3 days subsequently, followed by job 8 on days 13 and 14, because all these jobs 8, 9 and 10, their resource requirements are such that only one job can be scheduled on a particular day. You cannot have combinations of these jobs being scheduled by virtue of the limited resource availability that you have for these particular jobs. So these are the decisions in fact, and as a consequence what you find is that we schedule 9 on day 9 and 10 on day 10 and 11, 11 and 12. Subsequently job 8 has to be delayed, it becomes a critical job subsequently, and therefore it will further delay the project by 2 more days. So the project will now end after the job 8 is scheduled on days 13 and 14, and the final project duration is thus 14 days. So the schedule, the final schedule for this particular case would look something like this. This is the final schedule. The final schedule shows that we had put job number 9 on the day 9, and after 9 we had put 10, and if we had put 10 we could not have put 8 in parallel with it because it was not possible. Otherwise, had it been possible to finish 8 in parallel, you could have been able to finish the project by day 12, but now it is not possible. So we have to finish for job 8, job 10 to be finished, only then job 8 can be done. So job 8 is done in this particular fashion, and you have this is in again the slack, in the signs here, and ultimately what you notice is that we have been able to accomplish the project in 14 days, and the resource profile or the crew requirements are that on the 4th day and the 10th, 11th and 12th day you have a total resource requirement of 10, on other days it is less than 10. So this is a feasible schedule for this particular problem. In fact, for this particular problem, if you work out an optimal schedule, it so happens that this is in fact the optimal schedule as well. That means there is no schedule with a project duration lesser than 14 for a resource availability of 10 for this particular problem. Of course, this does not, this is a specially constructed problem by Wiest, maybe to demonstrate his procedure. So it's specially designed to generate an optimal solution, but the heuristic will not necessarily give you an optimal solution, as we indicated just now. Now if you look at this schedule, this is the final optimal solution, you will notice some very interesting properties of this particular solution. First thing is, if you recall that the notion of the critical path vanishes. Isn't this something very surprising? Because earlier a critical path was a path, unconnected path, it was this one, this and this was connected to this, and that was the critical path. Now there is no path in the problem which does not involve some kind of float. There is no path, this one, this one, this one, this one, isn't it? So is there a critical path in this problem now? What do you think? This is a very interesting thing which has happened, and in fact in all limited resource allocation problems you do not typically have a critical path in the conventional sense, and the notion of the critical path is however replaced by the notion of what is called a critical sequence. Now what is a critical sequence? Let us try to examine for this particular final, that means can you identify some set of activities whose durations add up to the project duration? You see, you can go 7, then you can go 4, then you can go 3, then can you go to anything else? Yes, you can go to 5, and then you can come to 9, and then you can come to 10, and then you can come to 8. Look at this same network and notice the following thing. In this very network, let us try to understand the notion of a critical sequence. Let us see what is a critical sequence. You see, you find go to activity 7, then you go to 3, then you go to 6, and from 6 if I add up to 5, and from 5 if I add up to 9, and if I 9 I add up to 10, and this I add up to 10. If I add up the durations of these activities, this is nothing but a critical sequence. Critical sequence 1, isn't it? Obviously these are the durations, this, and then you change. This is like saying there is no direct path. When you come to this station, you have to change the train and get into this one, and then come here, and then change the train again to go to this, and then change again to this. So these, and there could be many critical sequences. For instance, this was 3, 6. You could have gone, for instance, another way of going is you could have say 7, 4, and then you can go to 1, 1, and from 1 you can go to 9, you can go to 10, and then you can go to 8. So this is a critical sequence 2, right? For the same problem, I could have gone like this. Now suppose I want the sum of the durations of all these activities is 14, but mind you, these activities are not strictly related by the precedence that is found in a conventional critical path, but the duration, sum of the durations of these activities does lead to the total duration of 14, and it is not the critical path. The term that is used for such things is the critical sequence. So there are critical sequences, and there could be many critical sequences in a particular problem, but you will not have necessarily one connected path which will go to from one like we had in the earlier case. Here there is a vacuum, so you go here, then change again here, then. So this is another interesting feature really. The notion of the critical sequence is actually used in modeling the problem sometimes. Basically, when you are trying to model the problem, instead of dealing with the critical path, we have to deal with the critical sequences for such problems. So what we can see is that let's try to summarize the our discussions today. We find, for instance, that in summarizing the discussion today, we saw that the limited resource allocation problem was first of all contrasted with the resource aggregation and the resource leveling problems. I think the point that really has to be understood here is that the resource aggregation problem is the simplest problem, which does not involve any optimization. Resource leveling requires some optimization, but it does not worsen the project duration. And this is the most complicated problem, namely the limited resource allocation problem, where you are trying to conform to limited resource availabilities, and the objective is to minimize the project duration. So I think that distinction between the three problems must be clear. Then optimization versus heuristic procedures for the solution of the limited resource allocation and problem and projects were presented. It was seen that the heuristics were typically more popular in practical applications than optimization solutions. Then we looked at the comparative performance of 8 heuristics, and we found that heuristics based essentially on minimum slack or the latest finish time performed the best typically. A procedure due to waste based on very 3 simple heuristics was discussed, and an example problem was solved using the above procedure. And finally, some interesting things that came out from this procedure were that the notion of a critical path is not necessarily valid any longer. This is now replaced by the generalized notion of a critical sequence, and therefore we can. So I think we'll stop here. Thank you.